Hi everyone, thank you for joining in today. I am Manu Vajpayee from Samsung Research Bangalore, and I'm here to present our work titled Programmatic Optimization of Ad Pods for Maximizing Consumer Engagement and Revenue. Let us begin by looking into the intuition for this work. Samsung Ads is the fourth largest advertiser in the world. We are also in the unique position of being able to reach over 200 million devices, ranging from smart TVs, connected TV devices, and cross-media solutions. As a part of our user base, we have over 30 million smart TVs registered in US alone and about 70 million globally. The kicker is that 75% of audiences in the Samsung TV ecosystem are watching some form of linear TV. Since linear content is such a strong component of our CTV ecosystem, advertising optimally on the platform is a key target for us. This brings us to podding. I hope everyone here is familiar with ad breaks in traditional television, where our ads are grouped together between content. Podding is a similar concept for advertising on connected televisions. Ads are bundled together and inserted into content. This could be performed on the client or by server-side insertion. The benefits of bundling ads are not limited to just convenience for the publishers, where they don't have to worry about managing the constant switching between content and ads. It increases revenue for them by increasing the number of available impression opportunities. This is because more ad slots can be inserted into content without bringing extreme discontinuity. And it is beneficial for the impression consumers or audiences because it reduces fatigue and increases engagement. However, these two factors of revenue and engagement need to be balanced. Let's take a look at some hypothetical examples in the figure on the right. Number of ads are kept low in this case to illustrate the key points. Figure A is a simplistic case where only one ad of long duration was given the entire pod. This results in moderate revenue and engagement. Engagement here can be measured by firing trackers to log viewership of the ad. Figure B shows an indiscriminately generated pod which maximizes revenue but lowers the engagement because of a brand conflict. Figure C, on the other hand, is an optimal pod which balances revenue and viewer engagement. So, how do we ensure that our pods are going to be optimal? Let's try to formalize this problem. Podding follows a real-time bidding auction process. Similar to other forms of display advertising, a device requests the SSP or exchange for an ad. This triggers the exchange to send bid requests to DSPs along with targeting criteria. DSPs then reply with their bids and creative metadata matching with the targeting criteria as part of the bid response. Among the response attributes are creative IAB category and domain information. These received creatives are then evaluated based on their bid values, and some are selected for podding. The resulted pod is then inserted into the video for impressions. At the stage of ad selection, we are performing what we call an ad pod auction. Here, allocation of the ads also takes into account consumer engagement. For example, if there are K ads which are going to be a part of the pod, they must maximize revenue while ensuring that there are no conflicts between the constituent ads with respect to engagement. This is ensured by applying constraints on ad selection such that they do not share the same IAB category or the same ad domain. The ad domain constraints prevent repetition of ads from the same brand, thereby preventing overexposure. This can be modeled as a multi-objective knapsack problem with ad selection under constraints. These constraints are essentially business objectives. Let's take a look at some other constraints which can be applied before moving on to available solutions. First of all, revenue maximization itself is a constraint achieved by ensuring that the sum of bid values in the pod is maximized. Similarity between IAB categories of constituent ads must be kept low to reduce conflicts. Ad domains of constituent ads should also have low similarity. As discussed earlier, this prevents overexposure to the brand. Constraints can also be put on the frequency of exposure across ad pods. This further improves engagement and also minimizes ad expenditure for advertisers. We can also enforce distribution of ads in the pod. For example, all shorter ads at the end of the video, if this is desirable as per viewership analysis. And lastly, this can enable us to cater to specific requests by some partner DSPs who can ask for ensuring that all of their ads end up in the same pod. So essentially, any business objective can be replicated into a constraint in this multi-objective knapsack problem. Solving a multi-objective knapsack problem is not a new challenge. There are multiple algorithms which can be used to efficiently solve the same, in spite of the problem being NP hard. These algorithms can be classified into four categories: exact solutions, heuristics, learning-based solutions, and tailored greedy approaches. Common exact solutions are dynamic programming and backtracking, ant colony optimization, strawberry optimization, and evolutionary approaches are common heuristic solutions. There are multiple machine learning or deep learning based solutions, which include pointer networks and reinforcement learning based solutions. And lastly, there are tailored greedy approaches, which are created to solve a particular problem. In our case, we have selected three approaches to proceed forward. One is evolutionary algorithms, which are a heuristic approach, and backtracking and dynamic programming, which are exact solutions, which give optimal results in terms of both consumer engagement and revenue. We have also formalized a new greedy algorithm, which efficiently solves this problem. Before we move on to the results, let's look at our experimental setup. We have chosen two datasets. One is an in-house dataset, which is obtained from 7 days of auction logs, from which we extracted 15 different IAB categories, duration and bid value of ads. The second set is a YouTube ad dataset, which is a public domain dataset. However, this lacks bid information, which we have modeled with viewership. This contains 5,000 ads and their metadata. To proceed forward, we have constructed pods from ads available in these datasets. This is done by sampling in case of heuristic algorithms and ordered selection in exact and greedy cases. We have introduced constraints on IAB categories and revenue being the sum of the bid CPMs in the pods. We are using only one constraint in this particular case for engagement, because some algorithms like dynamic programming are very inefficient when the number of categories increases. In this case, repetition of IAB category is a mild engagement loss. In our approach with heuristic algorithms, in particular evolutionary algorithms, we have linearly increased the number of generations with pod size. We have given very high penalty for exceeding capacity in case of our pods. This is to ensure the duration remains within the limit. And we have put moderate to high penalty for similarity of constituent ads. Dynamic programming and backtracking are the exact solutions, which are used as benchmarks for profit, engagement, and computational complexity. And finally, we have implemented our greedy solution. So let's take a look at our greedy solution. We have developed two heuristics for greedy sampling of sorts. One is price to duration ratio, and the other one is price to duration ratio with price prioritize. PDR select slot with optimum balance of price and duration, while PDR WP gives less preference to very long ads, further preventing fatigue. PDR WP can be tuned to also remove very small ads. On the right is our entire algorithm, which starts with initializing the pod to adding these ads according to the different heuristics in a greedy fashion. Now, in order to estimate the performance of these algorithms, we generated 1,000 different pods using each algorithm and tested out the quality of these pods. In order to do the same, we have used the metric percentage deviation in profit, which measures non-optimal profit. Non-optimal profit is any deviation of the profit from the optimum value calculated by either dynamic programming or backtracking. The key point to note here is that if profit is not non-optimal, then so is engagement. This metric itself is similar to mean absolute percentage error, as can be seen in the results from both the data sets for different percentile values. DP, as expected, is giving 0 error. EA has a very high deviation from profit, while our greedy approaches show minimal deviation from profit. In case of a YouTube dataset, we are getting near 0 deviation in case of our second heuristic, although this may be because of some rounding errors. To look further into the performance of these algorithms, let's look at the distribution of errors. This distribution will give us a more holistic overview of performance. The key point here is that if the distribution moves far away from 0, then the algorithm has very poor performance. As you can see, EA is performing quite poorly in this case. On the other hand, our greedy approaches are near optimal. The key point of building these greedy algorithms was to figure out if we can reduce the computational complexity. This is because in real-time bidding systems, we have to include this computation along with several other components, and this running time has to be as low as possible. Here we have calculated the running time of these algorithms over 5,000 iterations for varying number of bits in pod. As can be seen, EA always performs the worst. Backtracking and DP show poor performance as the number of bits in pods increases. On the other hand, our greedy approaches are extremely fast. So they bring about two advantages. One is the quality of their results, which we saw earlier was quite good. The other is essentially running time, which makes them very suitable for deployment in an RTV system. To conclude, optimal podded ads offer a balance between revenue and consumer engagement. Optimizing ad pods can be modeled as a multi-objective knapsack problem. 4 families of algorithms can be used to solve MOKs. We have compared greedy, heuristic, and exact approaches. Our greedy approaches are nearly as accurate as exact ones, and the efficiency of greedy approaches makes them ideal for RTB deployment. Thank you for your time.